that's p here. I've moved 1 over y cubed to this other side. Okay, this is going to be 1 over y cubed dy. Then we can integrate. So this is going to give us p dp, that's p squared over 2. I hope you understand that. Derivative or integral of that is equal to integral of this, that's y raised to power minus 3, that's minus 3 plus 1 over minus 3 plus 1, then plus constant of integration c. So this is going to be p squared over 2 is equal to y raised to power minus 2 over minus 2, then plus c. So this multiplying all through by 2, we're going to have p squared is equal to minus y raised to power minus 2 plus, that will be 2c, that's still c. So from here we can get our p to be equal to c minus y raised to power minus 2, okay, all raised to power 1 over 2. Alright, so that is that about that. Then don't forget our p itself is this. Our p is dy dx. So that's what we just found now. So that means from here we can say that our dy dx is actually equal to this, is equal to c minus y to power minus 2 raised to power 1 over 2. So from here we can now solve our problem again. So that means we are going to have the variables separated. We can get the variables separated again because this carries only y, so we can have something like 1 over c minus y raised to power minus 2, okay, raised to power 1 over 2 dy is equal to the x. So we can integrate this. So this is the same as having integral of c minus y raised to power minus 2 all raised to power minus 1 over 2, okay, dy, to be equal to integral of this, that will be x plus k, another constant of integration. So like as expected, we should have two constants of integration. So let me continue here, not too far away. So we're going to have this, okay, c minus. So when we bring this to the denominator, it becomes minus. That's how we came about that minus. So as before, we're going to use the same approach, integrate with respect to the core. When we integrate with respect to the core, we're going to have c minus 1 raised to power minus 2, okay, all raised to power minus 1 over 2 plus 1, all over minus 1 over 2 plus 1, then in this case multiply by the derivative of the core divided by the derivative of the core. Will that work out? Let me check this again. So let's try to simplify this in another way. For instance, this c minus y raised to power minus 2, that is c minus y over 2. Let's just right now, that's c minus 1 over y squared. So we can put this as equal to y squared into, that will be c y squared minus 1. Okay, so if I have that, I can use that here instead. So instead of this raised to power minus 1, I'm going to have something like this. Proceeding from it is going to be it's going to be integral of, what we had here will now be integral of y squared over c y squared minus 1, then dy, so all of this raised to power 1 over 2. Now I've changed this, so this is going to be raised to power 1 over 2 dy is equal to x plus k. So we can now integrate this. Okay, so to integrate this, let's attempt a trigonometric substitution. Okay, the only thing we need to do to finalize this solution is to just integrate this, then equate it to x plus k. So let's integrate this somewhere. and see. Let's you can say let y equal to root c, okay, theta sec theta. You see why we're doing that now? You know we have cy square, yeah, so that by the time we square this, we're going to have c, then sec square theta, then minus 1. So that is going to be, no, this should be, sorry, at the end of the day I want to have something like sec square theta minus 1, so that I can equate that to tan square theta. We know that sine square theta plus cos square theta is equal to 1. So if you divide all through by that's by cos square theta, you're going to have this to be sine square theta over cos square theta, which is tan square theta, then cos square theta over cos square theta, that's 1, is equal to 1 over cos square theta, which is sec square theta. So because of this minus 1 I have here, I am looking forward to having something like sec square theta minus 1, so that I can equate it to tan square theta, okay, that denominator. And then let's see if that would help us out. So let's give it a try. Then we have this here, y squared. So if we actually make that substitution now, let's see what it's going to give you. If you can help us simplify this. But one thing we note here is that we need to clear off this thing completely, so that it becomes a trigonometric function at the end of the day. So I can say let's y to be equal to 1 over root c, then sec theta. So let's hope this works out. So if we have 1 over root sec theta, the idea is that when I square this, it's going to give me 1 over c sec square theta. Then when I multiply it by this cy square, when I multiply it by c, I'm going to have cy square to be equal to, so just sec square theta, and I'm going to have a denominator just sec square theta minus 1, which I can equate to tan square theta. Then at the numerator I'm going to have only 1 over c sec square, sorry, yeah, I'm going to have only 1 over c sec square theta. So let's see, that will now give me sec square theta over tan square theta. Will that work out? So yeah, so that may be able to help us out. So let's do this substitution first, okay? So let's do that. We have this to be integral of y squared over cy squared minus 1 dy. You know, everything here is to the power 1 over 2 dy. So we want to use this substitution. So if we are using this substitution, that means the theta, that means we are replacing the y with the theta, or replacing y with something theta. So dy d theta, that's the derivative of this with respect to theta. 1 over root c, that's still a constant. Derivative of sec theta with respect to theta is sec theta tan theta. You should remember this from your differentiation. And then that means that where we have dy, we replace it with 1 over root c, then sec theta tan theta d theta. So let's see how this goes. And now let's substitute there. Therefore I'm going to have integral of y squared over cy squared minus 1 dy. You know, all of this raised to power 1 over 2. This will be equal to the integral of, so y squared, don't forget this is our y, so y squared will be 1 over c sec squared theta, okay, from what we have done here. Y squared is 1 over c sec squared theta, and then we're going to have it divided by cy squared. Cy squared is going to now be sec squared theta minus 1. Then we're going to have dy, so everything here is to the power 1 over 2. Then dy is 1 over root c sec theta tan theta d theta. Okay, so this is going to give us integral of 1 over c sec squared theta divided by sec squared theta minus 1, that's sine square, that's tan squared theta. This is going to give us tan squared theta. We have this multiplied by 1 over root c sec theta tan theta d theta. So this is going to give me integral of course this is still raised to power 1 over 2. So when I take this square root of everything here, I'm going to have 1 over root c. Then I'm going to have it multiplied by square root of sec squared theta, that's sec theta, and square root of tan squared theta, that's tan theta. Then multiply by 1 over root c, then sec theta, again tan theta, then d theta. So I'm going to have theta, tan theta cancelling tan theta. I'm going to have 1 over root c, 1 over root c, that's 1 over c. Then I have integral of sec theta, that's sec squared theta d theta. Yes, we're good to go. So integral of sec squared theta is tan theta. So that's 1 over c tan theta, then plus some constants. Okay, we're leaving out constant of integration because we have put a constant outside here already. So this is just what we want to get. Alright, so okay, you can remember that derivative of tan theta is sec squared theta. Derivative of tan theta, that's derivative of sine theta over cos theta. Using bottom the top, that's cos, multiplied by derivative of the top, which is cos, that's cos squared theta, minus top the bottom, that's this, plus that's sine theta, multiplied by minus sine theta. That's how this became plus. Then that will be equal to sine squared theta all over bottom square, that's cos squared theta. And then we know that cos squared theta plus sine squared theta is 1, so this is 1 over cos squared theta, which is sec squared theta. So that's how we came about this. Integral of sec squared theta d theta is just tan theta. So we said that y was equal to 1 over root c sec theta, and then we now have our answer in terms of theta. Don't forget what we want to actually get is in terms of y. We want our answer to be in terms of y, so we have to return back to being in terms of y. So from what we have here, we had sec theta, we had y is equal to 1 over root c sec theta. So from here, we do know that y root c is equal to sec theta, and what we need to get is tan theta. We also know that tan squared theta is equal to sec squared theta minus 1, so that will be equal to sec squared theta is y root c, that's y root c. Okay, that's sec theta is y root c, so sec squared theta will be y root c all squared, then minus 1. So that means tan squared theta is equal to y root c squared, that's cy squared, then minus 1. Okay, cy squared minus 1 sounds familiar. Then that means tan theta will be square root of cy squared minus 1. Okay, and I take this, so these are our results. So from here we can now conclude that therefore the integral y squared over cy squared minus 1 raised to power 1 over 2 dy is simply equal to 1 over c tan theta, that's 1 over c. Then I have tan theta is this, that's 1 over c multiplied by cy squared minus 1 all raised to power 1 over 2. Okay, then I guess that is all about this integral. Yes, so okay, that's the integral anyways. But I noticed that was not a smart way to solve this problem, but it's fine, it's correct though. That's the correct thing. Let me write out the answer first. I just checked something here now that this is not so smart an approach to getting that integration, so I'm going to show you something now. But let's write out this answer first. That means our answer to the, so I've gotten this integral now, so our answer to the differential equation is just 1 over c into cy squared minus 1 raised to power 1 over 2, that's the integral, is equal to x plus k. So that's okay. That's the solution, and we're good to go. We have our two constants as before. But this integral, yeah, I was not so smart with the way I did this. So a better approach, because of the way this answer looks like something that could have been obtained directly. It looks much similar to this. It looks like something that could have been obtained directly from the question itself, I mean from the integral itself, without having to go through all of this. But it's fine if you don't understand this, that's okay. Basically what we have here is simply integral of y squared over cy squared minus 1, okay, raised to power 1 over 2 dy. So I did not recognize that we could have just taken the square root of y squared on its own. That would be y, then divided by then cy squared minus 1 raised to power 1 over 2 then dy. Okay, so we could have used all of these. Then we will notice that if you differentiate the core, if you differentiate this denominator, it was going to give us 2cy if we differentiate this denominator. So we can find a way to make the numerator 2cy. So we could have written something like this being equal to integral of, just pay attention, an integral of, let's say, 2cy. So to have that equal to this, we say this is 1 over 2c, so that is we cancel this, then divided by still what we have here. This is cy squared minus 1 raised to power 1 over 2 then dy. So we could have recognized this as having 1 over 2c, then 1 over 2c, then we have something like integral of 2cy, then we now have this here. This is cy squared minus 1 raised to power minus 1 over 2 dy. Okay, so again we can put this 1 over 2 inside. This is going to be 1 over c integral of 1 over 2 into cy squared minus 1 raised to power minus 1 over 2, then multiplying 2cy, okay, then dy. So we recognize that this here, this expression here, is just the derivative of this cy squared minus 1 raised to power 1 over 2. And then, we want to differentiate it. I mean that what we have here could just have been observed to be 1 over c into cy squared minus 1 raised to power 1 over 2. What do I mean by that? Because when you differentiate this, for instance, if you want to differentiate this, you bring down the power. Bringing down the power, this, if you want to differentiate, you are going to have 1 over c, then multiply by bring down the power, that's 1 over 2. Subtract 1 from the power, that will give you cy squared minus 1 raised to power minus 1 over 2, then multiply by derivative of the core, which is 2cy. So which is exactly what we had here, what we had here in this this. So we are integrating this back. I mean we're just dealing with this now. 1 over c is outside here, so that's it. So if you are differentiating this, you will get this, which is exactly what we have here. So just by observation that you may just have done it this way, then it's easier if you're able to notice that pattern here and derive this. It is shorter, you can write it out this way, it's correct, so just write it out this way. But if you don't, this is a good, even though it is long journey, this is a good approach to get the result also. And I have said before, and I'm finalizing this discussion on differential equation here, that if you can't remember how to solve a differential equation, just look at the options you are given. Try to see which of the options, when differentiated, will satisfy the differential equation. So you can pick that. When you have checked for all the options, check which of them satisfy the differential equation. Check that it has the proper number of constants. If it's second order differential equation, it should have two constants. Then check those options out that do not have two constants. Then the ones that have two constants, differentiate them and try to substitute in the original equation and see which of them satisfies the differential equation. So that's that for our discussion on differential equations. So I think we're good to go now. So you can just attempt the other questions on your own, just similar approaches to get them. All right, thank you. We'll conclude all that in the class.